Hey everybody, today we're going to look at one of the most important concepts in Max and in all of multimedia computing. In Max, this is called the matrix. Now, don't be thrown off by the name. That's just what it happens to be called in Max. The very same thing in video editing would be called a frame. In photo editing would be called an image. Alternately, it could be called a table, a data structure, a spreadsheet, or an array. It's all the same thing. It is the structure or the holder in which information is stored in the computer. And it has a particular shape and a particular format that we're not actually going to look at in this video. I just want to introduce the concept of the matrix because it's going to be a key concept for the rest of the semester, the rest of the tutorials. So let's start out. I have some small images of Space Invaders. Here's a Space Invader. And we see that when I drag it into my patch, it comes in blurry. And that's not actually what it looks like. That's because this is an extremely low resolution image where each square we see is actually a separate pixel. So the object that allows us to drag images into a patcher is just blowing it up to the size of the window that we have. But if we look at this at the actual size, by going down and unchecking scale to box, we'll see how tiny it is. That's how big the image is. And that's why it's blurry when it's blown up. So we can scale this down quite small. We don't need to worry about it. We'll put a button here, and I'll introduce a new object called the jit.p window. And the jit.p window is a window that displays matrices. So if we connect that, it looks a lot like the fpic, which is the object that we create when we drag an image into our patch, but it's not the same as an fpic. Lock our patch, click the button. Now we see this image, right, without the blurriness. We see the image with crisp edges, and each colored square represents a pixel. And so this is the reason why I chose a Space Invader. I wanted to choose a very low resolution image, an image made up of very few pixels, because that makes it much easier to demonstrate how the matrix works. So I created a couple of helper objects for this tutorial. You can download them. There's max compressed text in the comments on YouTube, and they're also downloadable from the class Blackboard site. The first one is j.matrix convert. And this is a very simple helper object that by holding down the shift key we can insert here. And j.matrix convert just changes the format of our image so that we can use it in this tutorial. It also has a couple of helpers. If you attach a floating point number box to the second inlet, and you also attach the right outlet to your jit.p window, you can just use this to proportionally resize your P window. Because if you resize a P window by hand, you can change the aspect ratio, and so you lose track of what your image actually looks like. Is it a tall and narrow image? Is it a wide image? Using this box, we say, aha, it's a rectangular image. And we can look at the resolution of the image using an object called jit.fps GUI. And jit.fps GUI tells us a bunch of stuff about a matrix. It tells us the number of frames per second. This is a still image, so it has 0 frames per second. But it can also tell us the dimensions of the image. So if we send the image again, we see this is a 13 by 10 pixel image. That's an extremely low resolution image. It can also tell us about the number of planes in the image. This image contains 3 planes for the colors red, green, and blue. Now, the reason why we need the j.matrix convert in part is because the starting image has 4 planes. and we don't want to deal with the transparency plane for the purpose of this tutorial, so we're eradicating it. And anytime I give you an object like j.matrix convert, you can always double click it, dive inside, and see what I'm doing inside. A lot of this is more advanced than we're going to cover in this semester, but it's there if you want to study it and ask questions about it and pick it apart and find out why it works. I'd be happy to discuss that with you. But this is part of the reason why I create these helper objects for you, is that there's a lot of detail in here that there's just not time to go over in the course of this semester, and it's not that important right now. So we can bring in a couple more of our Space Invaders here. They all come in looking blurry. Using Command D, I can duplicate an object with spacing. I'll shrink these down because we don't really need to see them large. And I'll connect them all to my j.matrix convert so that I can switch between my various Space Invaders. And if we switch back to dim here, we can see these are all 13 by 10 pixel images, extremely low resolution images. So why are we looking at Space Invaders? Well, because I want to talk about what the matrix is. The matrix is the best of all of these terms. The best descriptor for what a matrix is it's a spreadsheet. If you've worked in Excel, you understand what a spreadsheet is. It's a table that holds numbers. So there's another one of the terms, table. And that's exactly what a matrix is. That's exactly what a frame of video is. That's exactly what an image is. The computer only deals in numbers, and a matrix is numbers. And there's an object that allows us to see the numbers inside a table. It's called jit.cellblock. And that creates something that looks like a spreadsheet, a table, jit.cellblock. So when we connect a matrix to a cell block, send the image through, we get to see the numbers that are stored in the table. And we see that this corresponds to our image. So here we have 0, and that corresponds to a black cell. Here if we go down 1, 2, 3, 4 pixels down, 1 pixel over, we see there's a 0.85, and that corresponds to this red square right here. And if we go over to the next square to the right, 0.53, that corresponds to this blue square. 0.97 corresponds to this white square. So what do these numbers represent? Well, we are only seeing one number, but we know that there's 3 numbers here. We know that there's numbers representing red, green, and blue. So what we're seeing here is just the first layer of numbers. We're seeing the numbers that correspond to red. So again, I've made another helper tool to help us visualize this more effectively. And it's called j.cb_format. Holding down Shift, we can insert this into the patch cord and send a Space Invader through. And now this is what j.cb format does. It actually colorizes the cells of the cell block so we really can see much more easily what's going on. So we really can see that this is, quite clearly the same image. And here, the black has 0 red in it. The red has 80% red. The darker red has 70 or 60% red. The yellow has 80 or 90% red, 0.9, 0.8. And we're only seeing the red right now, but if I make this wider, we'll see the red, the green, and the blue values in each cell. So again, why are we looking at this? Why does this matter? This matters because we're trying to understand what a matrix is. A matrix is an image, and much more than an image, we'll find out later. It's a table of values. It's a data structure, meaning it's a thing that holds data, holds information. And it's a spreadsheet. It's quite literally a spreadsheet. But the difference between this kind of spreadsheet and what you might see in Microsoft Excel is that this spreadsheet can hold 3 or more values in the same cell. In an ordinary like accounting spreadsheet or inventory spreadsheet, you're only putting one number in a cell. But in these cells, the cells have what are called planes. And the planes, in this case, are red, green, and blue. There's a plane for each color. So each cell has 3 values in it, 3 planes in it. Now, this is a great moment to stop and really make sure that you understand truly what's going on here, because this is the basis and this is the foundation of a ton of work that we're going to do moving forward. So really wrap your head around this. Really, if you're saying, oh, I'll figure this out later, oh, I'll understand it later, you won't. This is your opportunity to really grasp what the matrix is. Think about these equivalencies. Matrix is the same thing as a frame of video. It's the same thing as a still image or a photograph. Same thing as a table. Same thing as a data structure, a spreadsheet, or array. All right? And a cell, one of these, is the same as a pixel. And it contains multiple planes, a plane for red, a plane for green, a plane for blue. But also understand that these don't have to mean red, green, and blue. They happen to in this case because this is an image. But these are just numbers. And we're going to see more about that later. So I've created another helper object that is going to go even further into explaining what is inside this matrix. It's called jit.matrix viewer. And it pops up this window called matrix viz. It has a whole bunch of inlets. We can take our image, and the image does come out of the bottom of a jit.p window, out of the left outlet. So we can just pass right through our jit.p window into matrix viewer. Send one of our Space Invaders in, and we'll need to hook up some controls. We'll need a float connected to the second inlet called layer separation. We don't really need the third inlet connected, but might as well connect it while we're here. We need a j.translate object connected to the fourth inlet, so we can adjust camera location. And then we need 6 toggles created with the T key connected to the next 6 inlets. 1, 2, 3, 4, 5, 6. And you can see what these are as you mouse over them. Enable the red, enable the green, and then we'll talk about these other ones later. And what I've done here is I've taken the matrix and I have spread it out and made cubes out of every one of the pixels so that we can see more clearly what I mean by planes. Red, green, and blue being separated into planes. So we can create some camera views for our j.translate. Create a little screen landscape here. And we're all familiar with j.translate from the animation tutorial. I'm just using this to move my camera around so that I can go to a wider front view or a top view. And you can see now my pixels are rendered as 3-dimensional cubes. And the reason why I'm doing this is because I want you to see that the color of each of these cubes is made up of a red layer, a green layer, and a blue layer. So this j.matrix viewer actually spatially separates the three layers and allows me to turn on and off the different layers. So we can see our Space Invader here has red eyes and white surrounding the mouth. So let's take a look at the red layer. I'm going to turn off the green layer, turn off the blue layer, and you can label these to make things a bit more readable if you want. Put a comment, red, green, blue. And I'm leaving the red layer on. And we can see that the red value is high when the pixel is red or the pixel is white. The red value is lower when the pixel is purple. But if we switch to our green layer, we see the green layer, there isn't a lot of green in this image. The only place where there's a lot of green is in the white, because white is the presence of red, green, and blue. Maximal red, maximal green, maximal blue. And if we take a look at the blue layer, it's very similar to the red layer, with the exception that the red eyes do not have a lot of blue in them. You can see the red eyes are quite dark. And I can pull this image back together. I'm going to just select this number box, go to the inspector here, and at the bottom of the inspector, I can set a minimum value for the number box. I'll just set that to 0. So now I can stop at 0, brings the image back together. So let's take the yellow monster here, and we can do the same thing. We can fly over to the right, separate the red, green, and blue, and take a look at what's happening in each of those layers. I can turn off the green and the blue, and when I look at the red layer, I see that the 3 blue eyes don't have a lot of red in them. However, the yellow has quite a lot of red in it, and the purple has some red in it. When I turn on the green layer, I see that it's very similar to the red layer in that the yellow has a lot of green in it, the blue eyes don't have much green, the purple areas don't have much green. When I look at the blue layer, I can see that the blue eyes certainly have a lot of blue, and the purple certainly has a lot of blue, and everything's got some blue in it. These images are not very nuanced in their color, and yet we still see that we're not dealing with simple values like 1, 1, 0 to get a yellow. We're dealing with something like 0.89, 0.89, 0.43. The fine gradations in these values are what give the color its very specific quality. 110 is a yellow, but it's not this yellow. And 001 is a blue, but this is a very specific kind of cornflower blue that is achieved through exactly this combination of numbers, 0.29, 0.36, 0.62. So through these two views, really take some time with this, really explore and make sure you feel comfortable and solid about the fact that these 3 planes of information are stored in this structure that we're calling a matrix. That's the introduction, and now here's the really interesting thing. Right now, these values are obviously representing color, but they could also represent position. So for instance, take a look at this. What are we seeing here? we're seeing the values in the matrix representing not just color, but also position in three-dimensional space. What do I mean by that? I mean that this 0.89, 0.89, 0.43 means not only 89% red, 89% green, 43% blue, it also means 0.89 meters to the right, 0.89 meters down, and 0.43 meters towards the camera. And similarly, this 0.29, 0.36, 0.62 not only creates this blue color, it also means 0.29 meters to the right, 0.36 meters down, 0.62 meters towards the camera. Or actually, in this case, I believe it's away from the camera. Take a look at the top view. Yes, the higher value is moving me away from the camera in this particular example. But this is not very interesting. There's only 3 colors in this alien, so even though there's 130 cubes here, they're all confined to 3 locations. And this is true of all of our aliens. When I switch to this alien, there's a little bit more variation in color, but there's basically 3 categories of color. There's the yellows, the bright reds, and the darker reds. And we're seeing here that the same numbers that create red, green, and blue can also be used to represent horizontal position, vertical position, and distance from the camera. It's not really distance from the camera, it's distance from the center, but since our camera is looking at the center, it functions as distance from the camera. So this is instructive, it's simple, but since there's so few colors, it's hard to get a real intuitive sense of how this works. So I've added a feature to the j.matrix _ convert, a button that attaches to the third inlet that is going to colorize our Space Invader a little bit more interestingly. Just click that a couple of times till you find an interesting color palette. And now there's a much larger range of colors mapped to our creature here. And you might have to resend the Space Invader and then click this button a couple times. And now we can get a much clearer sense of how these values are representing both color and position. Since redness is the horizontal position, the more red content there is in a pixel, the further to the right it will be. The more green content there is in a pixel, the lower on the screen it will be. And the more blue content there is in a pixel, the further away from the camera it will be. So play with this a little bit and really try and get a feel for what this means, that the values are representing not only color, but the same values are also representing position. Now, you don't have to use the same values to represent color and position. In fact, you almost never will. That's not the point of this. The point of it is to demonstrate that these are just numbers. They're simply numbers, and they can be applied to color, 3 numbers, red, green, blue. They can be applied to position, 3 numbers, X, Y, Z. They can also be applied to scale. I'll add a few more notes here. We'll call this position, scale, and rotation. Don't forget to save as you go. So now, the same values that are coloring the cubes and positioning the cubes are also scaling the cubes. Let's go back to one of our basic Space Invaders here. We have 3 colors. We have a blue, a yellow, and a purple. And blue is Z position, but blue is also the depth of the cube. So the more blue it has, the deeper it will be. We can see that from the top view, right? The more blue content in a cell, the further away from the camera it will be, and the deeper the cube will be. Take another, and here we can see the more red content a pixel has, the wider it will be and the further to the right it will be, right? Redness, X horizontal position, and width are all the first number in the triad of numbers. And in this particular instance, we're matching them. We're keeping them all the same. We're keeping the color and the position and the width the same just to demonstrate the concept. So let's add some more interesting coloration. And we can see how the arrangements become much more intricate. Redness moves things to the right, makes them wider. Greenness moves things down and makes them taller. Blueness moves things away and makes them deeper. And we can add rotation as well. Where redness, X position, width, and rotation around the X-axis are all represented by the same value, by the first value stored in the cell. Green, vertical position, height, and rotation around the Y-axis are all stored in the second location in the cell. And blue, Z position or distance from the center or from the camera, the depth of the shape, or you can think of it as the thickness of the shape, and its rotation around the Z-axis are all controlled by the third number. And so spend some time playing around with this and see if it will help you get a understanding of how these things interact with each other. Right, you can see that as this shape becomes pinker, it also rotates its face towards the camera. That's because the first value in the triad is increasing. So it's increasing redness, it's increasing the horizontal position, it's increasing the width, and it's increasing the rotation around the X-axis. Here's another example. So you might be asking yourself at this point, okay, that's fine. I get it, or I sort of get it, but how do I do this? How do I implement it? Well, that's not what this particular tutorial is for. This particular tutorial is to introduce you to the concept of the matrix, to introduce you to the concept that these triads of numbers, and they don't have to be triads, you can store an arbitrary number of values in a cell, but triads are quite common because they correspond to all of these common uses. This patch that you built while doing this tutorial is a chance for you to wrap your head around these ideas so that we can then go on and figure out how to implement them, and of course implement them in a much more interesting and sophisticated way than I have in this very simple demo here.